Welcome back to the deep dive. Today we're jumping into something a bit different, a real-time mechanical puzzle. It all starts with this really baffling alarm on an industrial machine, the Okuma 6. The alarm code itself is 118131 ALARM-A MCS DIFF over XBaxis FFFCEFD.
Quite a mouthful, right?
Definitely sounds cryptic.
And our source material for this is, well, it's fascinating. It's essentially a raw chat log. You get to see technicians and engineers talking back and forth, really racing against time to figure out what's wrong and get this machine fixed.
Right, it gives you that fly-on-the-wall feeling.
Exactly.
So our mission today is basically to unpack what that alarm code actually means. We'll follow their diagnostic journey step by step, see the mechanical problems they uncovered, some quite surprising, and maybe the most interesting part, see what happens after the fix. Because, fixing one thing often reveals another. Yeah, that's often the case, isn't it? So the big question for you listening is, what does this intense troubleshooting process really tell us about the hidden complexities inside these machines we depend on every day? And like you said, how does a supposed fix sometimes just open up a whole new can of worms? Dava, the cryptic alarm. MCS DIFF over XBaxis. Okay, let's start right there with the alarm. 118131 alarm, MCIF over XBaxis FFFCEFD. Sounds like, I don't know, secret coordinates or something. But for the Okuma 6, it's a very specific signal. What's it actually saying?
Yeah, it does sound like code. So MCS DIFF, that stands for Machine Control System Differential. And it's basically flagging a large positioning error, specifically on the XBaxis here.
Okay, a positioning error. What does that mean in simple terms?
Think of it like this. The machine's control system tells the XBaxis, okay, move to this precise spot.
Yeah.
But the axis doesn't quite get there, or maybe it lags behind significantly. That difference between where it should be the commanded position and where it actually is, well, that's the following error.
Okay.
And when that gap, that following error, gets too big, bigger than the allowed limit, bang, the machine throws this alarm. It's a safety mechanism, really. And that string at the end, FFFCEFD, that's like a snapshot of diagnostic data taken right at the moment the alarm happened. Super useful for the techs.
Gotcha. So when this alarm goes off, bells ringing, lights flashing probably, where do the technicians even start? What are the usual suspects for this kind of error?
Well, right out of the gate, the team had a list of possibilities, the common culprits. Things like the ballscrew itself could be damaged, or maybe a bearing associated with it.
Makes sense.
It could also be the motor driving the axis or the inverter unit that controls the motor's power. Sometimes, believe it or not, it can even be an issue in the software, like a corrupted servo data file. So they had a few places to look initially, too. The diagnostic quest, from symptom to suspect.
Okay, so the alarm's active, they have their list. What were the very first practical steps the team took? I see Fabian Acheval jumped in pretty quickly in the chat.
Yeah, Fabian immediately confirmed, okay, it is the Okuma 6 showing this specific alarm, and then asked for something crucial. The latest raw data of Ballbar test to review it.
A Ballbar test. What's that involve, and why was it the go-to diagnostic here?
A Ballbar test is, it's a really high-precision tool. It basically measures how accurately the machine can move in, say, a perfect circle or along perfectly square paths. It maps out the machine's geometric accuracy.
Okay.
And the results from those initial Ballbar reports were, well, they were revealing. They showed right away that the squareness looks off. In fact, it was 4 times out of tolerance, which is quite a bit.
4 times?
Yeah. And they also saw other things like scaling mismatches, meaning distances weren't quite right along an axis, and uneven backlash, which is like slop or play in the movement, all definite signs of mechanical issues.
Then Fabian suggested something really hands-on, almost old school. Actually putting a hand on the turret while the faulty XBaxis was moving. Seems basic for such a complex machine.
It does. But it's surprisingly effective. What you should feel is just consistent, smooth motion. If you feel anything else, weird noises, grinding, any kind of jerky or irregular movement, it tells you something physical is wrong.
Like a mechanical binding or something.
Exactly. It helps differentiate between, say, an electronic signal glitch and a real physical hang-up in the mechanics. Quick sanity check, really. And there was another clue in those Ballbar tests, something called a discontinued plot. That happens when the test sensor gets pushed either all the way in or pulled all the way out during the test.
Meaning?
Meaning the machine's movement is so far off that the sensor literally runs out of travel. If you can't even get the sensor centered to start the test properly, it's a very strong sign that, yeah, the machine has issues. Big issues.
And context matters too, right? Duarte Obed chimed in, asking if this was the same machine where they had changed the ball screw earlier this year.
Right. Turns out, Looking at the work orders later, it was actually bearings replaced back in November 2023, not the whole ball screw. But it shows they're thinking about the machine's history. Was this a recurring problem?
Gorte also mentioned something about motor plugs maybe not being in good shape or even missing, another potential variable.
Exactly. You have to consider all these factors, the history, the related components. It's detective work. 3, the smoking gun, bearings and pins. So gathering all these early clues, the alarm, the Ballbar results showing poor squareness and backlash, the field test, the history to field, the team reached an initial pretty strong conclusion.
Which was?
That it was looking very likely that the XBaxis ball screw assembly needed to be replaced. That seemed to be the most probable culprit, fitting the symptoms.
A major repair replacing a ball screw.
Oh, yeah. And because that takes time, they immediately discussed a workaround. Just shifting operations to use only the upper turret of the machine, assuming he has 2, to try and keep some production going while the XBaxis, likely part of the lower turret system, was down for repair.
Makes sense. So they start the ball screw replacement, and as they get deeper into the machine, what they actually find. Did the reality match the initial diagnosis?
Well, this is where it gets really interesting. As they disassembled things, they found a couple of significant issues. First, some crucial taper pins were not in good condition.
Taper pins.
Yeah, these are item number 45 on the diagrams, apparently. Part number C0201080361, located in the lower turret. They're small, but their job is critical. They ensure the turret is perfectly aligned, perpendicular to the X-axis cross-slide. If they're damaged, alignment goes out the window.
Okay, so damaged pins. What else?
Even more telling, they found a lot of shavings near the bearings. Metal shavings are never a good sign. It points to friction, wear, something grinding itself apart.
And the bearings themselves.
That was the big one. They found the bearings, specifically NSK 30TT62DB, which are high-precision angular contact thrust ball bearings, were completely destroyed. The report describes a complete failure of the bearing cage.
The cage. What does that do?
The cage is what holds the individual ball bearings in place, keeps them evenly spaced within the bearing races. Here, the cage was described as destroyed. The ball bearings were loose, just rattling around, and that almost certainly meant damage to the races, too. The tracks the balls run in. It was pretty catastrophic for the bearing.
Right. So this seems like the smoking gun. I see Fabien Acheval made a pretty definitive statement in the chat after this discovery.
He did. He stated very clearly, the catastrophic failure of the bearing cage is the direct cause of the machine's alarm. 118131 alarm. A. MCS DIFF over XBaxis FFFCEFD.
Okay, so connect the dots for us. How does a failed bearing cage lead to that specific positioning error alarm?
It's a clear chain reaction. First, the cage failure happens. The cage breaks apart. This allows the ball bearings inside to bunch up, jam against each other, and against the races.
Right, they're not spaced properly anymore.
Exactly. This jamming causes the ball screw to seize, or at least become incredibly hard to turn. It can't rotate freely like it's supposed to, but the motor is still trying to turn it, following the commands from the control system.
So the motor thinks it's moving, but the screw isn't really turning smoothly.
Precisely. So you get this huge position error building up very quickly. The commanded position races ahead, while the actual physical position lags way behind because the screw is binding up. Once that error exceeds the preset limit,
the MCS DIFF alarm triggers.
Bang. The alarm triggers to stop everything before more damage occurs. So yeah, that failed bearing cage was absolutely the root cause of that specific alarm sequence.
And looking back at those work orders, again, WO1009715115 was for this current ball screw change. But the previous one, 101-962-5866 from November 23, was only for bearings. And the same alarm happened back in August 23, too.
Yeah, it suggests this might have been a developing problem, or maybe the previous bearing replacement didn't fully address an underlying issue, perhaps related to the ball screw or alignment, that led to this subsequent, more catastrophic failure.
It definitely seems like a recurring weak spot for this Okuma 6. 4. The post-repair paradox. A new twist.
Okay, so they found the trash bearing, replaced the ball screw assembly, which includes new bearings. They put it all back together. What was the immediate result? Did it fix the problem?
Well, the initial reports after the ball screw installation were actually quite positive. The feedback was that the movement of the XBaxis is really good and smooth. Sounds promising, right?
Yeah, sounds like case closed.
Not quite.
Yeah.
This is where the paradox comes in. They ran a new Ballbar test after the repair. And the results were mixed and honestly a bit surprising. On the one hand, the x-axis looks good in terms of its individual performance, likely indicating the backlash, and perhaps some smoothness issues were resolved by the new ball screw.
But the squareness issue was still there. And here's the kicker. It had actually gotten worse.
Worse. After replacing the core component causing the initial alarm, how is that possible?
It had worsened significantly. The report shows it went from negative 285.12 micrometers per 300 milliliters before the repair to negative 477.000 micrometers per 300 milliliters after. That's roughly a 67% increase in the squareness error.
Wow. So fixing the bearing and ball screw somehow made the machine less square?
It seems that way. And this really highlights something crucial in complex repairs. Fixing one major obvious problem like that seized bearing can sometimes unmask or even exacerbate other underlying issues that were perhaps being compensated for or simply weren't the dominant error before.
Right. Maybe the old worn components were deflecting in a way that partially hid the squareness problem.
Possibly. Or the process of replacing the ball screw itself might have slightly shifted the alignment. It's hard to say for sure without more data, but the result was clear. A worse squareness deviation.
And remind us, what's the practical impact of this negative squareness error? If the machine isn't square, what happens to the parts it makes?
Well, negative squareness means the angle between the machine's main axes, say X and Z, is slightly less than 90 degrees. So if you try to machine a perfectly square pocket or cut a perfectly flat face that needs to be perpendicular to another face, it won't be.
The corners won't be true 90 degrees.
Exactly. Your parts won't be geometrically accurate in that way. For precision work, that's a big problem. So faced with this new, worse squareness, what could be causing that? The source material lists several possibilities. Things like maybe an axis itself is slightly bent, or there's still some misalignment. Perhaps the axes are drooping under their own weight, or issues with the guideways or the Gibs. Those are adjustable components that ensure smooth, straight movement along the ways.
Could even be the machine isn't perfectly level on the floor, right? Or the new ball screw itself.
All possibilities. And they found another related issue, too. A scaling mismatch, this time in the Z-axis, about 0.00047 inches.
Okay, so now they have two issues post-repair. The worsened squareness and this Z-axis scaling mismatch. What's the plan now?
Well, the team recognized that both of these issues, the squareness and the scaling mismatch, are contributing to the overall circularity being out of tolerance that the Ballbar test measures. You can't get perfect circles if your axes aren't square and moving the correct distances.
Right, they compound each other.
Exactly. So to get the machine performing better than ever before, as they put it, they need to address both problems. The next proposed step seems to be focusing on the Z-axis, specifically looking at its Gibs and guides.
Why the Z-axis specifically?
Particularly because that negative scaling error suggests the Z-axis might be over-traveling relative to the X-axis. Adjusting the Z-axis Gibs might help correct both the scaling and potentially influence the squareness relationship between Z and X.
So the investigation continues, just shifting focus.
It does. They're clearly still working through it. On a positive note, they double-checked a belt noise issue that had been mentioned and confirmed that's gone now. And, crucially, the machine hasn't thrown any other alarms or shown new defects since the ball screw change. So progress, but still more tuning to do. The plan is also to let an AI process run to help generate a complete troubleshooting guide based on this whole saga.
Oh, what a journey. We went from this really specific, almost obscure alarm code.
Yeah, the MCS DIFF over XBaxis.
All the way down to finding a completely destroyed bearing cage inside the machine. And then, after fixing that catastrophic failure, uncovering this deeper, unexpected issue with the machine's fundamental geometry, the squareness.
It's a fantastic example, really, of how interconnected everything is inside these complex machines. You fix the loudest problem, the bearing seizure, and suddenly you can hear the quieter problem, the misalignment that was there all along, or perhaps was even slightly changed by the repair process itself.
It shows that diagnosis isn't always linear. It's often peeling back layers.
Definitely. It requires, a different level of critical thinking. You solve one thing, then you have to reevaluate what else could be going on.
So it leaves you wondering, doesn't it? What does digging into this kind of intricate, real-world problem-solving process tell you about tackling complex issues in general? That sometimes the solution you find is really just the start of asking the next deeper question.